Okay, good morning, everyone. You should be able to hear me. So if you do hear me, give me a thumbs up so I can see that you actually are hearing me. Very well, thank you. Um, so let's get started. Today we're going to finish some of the discussion of potential energy and start with conservation of energy for conservative forces and for non-conservative forces. Um, just as a reminder, we went through a couple of topics here in this chapter and the previous chapter. So we introduced work, which is the energy transferred to an object by a force working on it. We introduced kinetic energy, the energy of an object, of a moving object, by virtue of its speed. So the work was F dot the displacement for constant forces, and there was an integral, there was a differential expression for that as well. Kinetic energy is 1/2 mv squared. And then we introduced potential energy. That's the ability of a system to do work. So that's the energy that an object has by virtue of its position, or by virtue of its, by virtue of its position in most cases. So just as a reminder, we determined that a force is conservative. So conservative forces are those forces that can be described by this potential energy. Not all forces can be described by a potential energy. Only conservative forces can be described by a potential energy. And what mathematical criterion is there for a force to be a conservative force? Well, in a conservative force, the work done by the conservative forces, so F dr, this infinitesimal amount of work, must be an exact differential. That means that this must be the differential of something, so that the integral becomes trivial and just depends on the initial and final point. And that gave us, or calculus gives us then, the expression that dfx dy must be equal to dfy dx. That's the condition that must be satisfied for conservative forces, for a force to be conservative. And so we can see, for example, if we use F is minus mg y hat for gravity, then we'll see that this is essentially Fy times y hat, right? So dfy dx is equal to 0, and dfx dy is equal to 0. So both of those are the same. So indeed, this is a conservative force. Gravity is a conservative force with, as potential energy, u as a function of the height is mg times the height, where we've set as a reference point that u at the height equal to 0 is defined to be 0. Remember, we needed to set that reference point. So we can take this this description, though, a little bit further. If we start again from our dw, or infinitesimal amount of work, we know that we can introduce the potential energy that way. We can write du as minus dw. That's how we introduced u, by relating it to the work, right? We introduced the potential energy by saying it had to be the negative, the change in potential energy had to be the negative of the work. So that's going to be minus f dr. And we can actually choose any direction if we're looking at a change in potential energy. We can describe if we're thinking, for example, of something that is moving along a single axis, we can choose our dr to be in this direction or in that direction if we're just considering ourselves as moving in a an environment where there is a potential energy, or if we're in 2 dimensions in an xy plane, we can pick any direction dl and consider what the change in potential energy will be if or force along that the direction dl. So that will be minus f dot dl. This is actually the L component of dl, right? If there is a force here, or force dotted with the vector dl, is going to give us in magnitude the component of the force along that L direction times dl. And now if we look back at what we have here, we have du is minus FL dl, so we can actually rewrite this as FL, or the component of the force along a direction L, is minus du dl. It's the derivative of u along that L direction. So the derivative of u along the direction L gives us the component of the force along direction L. So if we again, if we now start from u is mgh, and I'm going to replace this by y, or not the unit vector, mgy. So for gravitational potential energy, if this is or potential energy, and it depends on y, but let's assume this could depend on x and y in general, right? It doesn't depend on x here, but this could depend on x and y. I can now say that the force along the y direction is minus du dy, so that's minus m times g, which we know is correct. The force along the x direction is minus du dx, so that's 0. That we also know. But this is even more powerful if we have, again, a block sliding on an inclined plane with an angle theta. If we're now looking at the direction here, we've introduced this as a direction s before. We could calculate the force along the s direction as minus du ds. Now it becomes a little bit more complicated because now we have to write this as dds of mgy, but we can write y in terms of s. We've done that before actually. Y is s times the sine of theta, right? So this is minus dds of mgs times sine theta. So that will be minus mg times sine theta. And that gives us now the force, or the component of the force due to gravity. So this is the weight itself. So that's going to be the full force. But the component along the s direction is going to be negative, which we see by virtue of the minus sign here. And it's going to be decreased by a factor of sine theta. So this becomes very powerful. This expression here becomes very powerful because it allows us for any potential energy to determine from that potential energy in which direction the force will point, and what the magnitude of the force will be. And of course we can apply it to any force, so or any potential energy. Let's say we know that our potential energy is so another example, if our potential energy is 1/4 cx to the 4th, let's say, what's the force? Well, we know that the force will be entirely in the x direction only because there's no dependence on y or z or any other variable here. So then f of x will be minus du dx, and that is minus 1/4, well, the 1/4 will actually disappear with the factor 4, so it will be minus cx to the third power. And this will be in the x direction, or I guess we're writing this here as the x component, but f as a vector will be minus cx to the third in the x direction. So starting from the potential energy is sufficient to determine what the forces are. There's in other words, for conservative forces, all of the information is in the potential energy to determine what the force is, which of course makes the potential energy a very powerful concept, because it essentially includes in a single functional description, in a single function, it includes all the information that for a force we would have to put into three different vectors. So in this case, c is just a constant, essentially taking the role as k in our spring force. In 3 dimensions, you'll actually see us use, if you've done any kind of vector calculus, which I guess probably not yet, but you'll see the notation that the force is minus the derivative of the potential energy, where this inverse triangle with a vector over it is the nabla symbol, which essentially gives us a derivative in 3 dimensions. So it turns this potential energy, which is a scalar quantity, it takes a derivative in such a way that it turns it into a vector. So no need to think about this. But this is the kind of notation that you'll often see. If we think about this potential energy a little bit more, we can get out our graphing calculator, and you can draw the value of the potential energy as a function of x. And this is an x to the 4th force, so it will go up to infinity at positive x, it will go up to infinity at negative x. It goes through 0 at the origin, right? We can pick at some point here, let's say at some point x here, we can look at what the value of the potential is. But more importantly, we can look at what the value of the derivative is there. So in this case, du dx will be positive, right? I mean, it's rising. So that means that minus du dx will be negative. And why do I write this as minus du dx? Because that's f of x. So f of x will be negative. We'll be pointing in that direction. If we look at another point here, the derivative of u to x is going to be negative here. So minus du dx is positive. So in this case, the force will actually be pointing in that direction, the positive direction. So what will happen here is we have a potential energy that looks like this, and the force that this potential energy describes is pointing always to the minimum in the potential energy. Essentially, you can start to think if objects are moving on their own, and this potential energy is the only thing that describes their motion, then you can think of this as objects are moving on this potential energy curve, and they're trying to get to the minimum of the potential energy curve. At the point when they're in the center here, the force is going to be 0, because the first derivative to x is 0, because we're in a minimum. So we're going from larger values of the potential energy to smaller values until we reach that equilibrium. Of course, at this point we may have kinetic energy, and we can shoot past the minimum, and then there will be again a restoring force on the other side. So this is an example of what this restoring forces in general will look like in an energy diagram where we have the energy versus position. And of course, in this case, for one coordinate x, we could make these kind of drawings with a little bit more precision so that they're clearer in two-dimensional problems as well. So then we'll have energy surfaces that are in the vertical direction is going to be the potential energy, and x, y will be the horizontal coordinates over which we draw the surface. Okay. And then, of course, you can do this for three-dimensional things as well, but then, of course, you can't draw it anymore because you can't draw height maps over 3 dimensions because then you need the 4th dimension, and it's very hard to draw 4 dimensions on a 2-dimensional sheet of paper. So, let's take a step back. Oops. Let's take a step back here and think about how we would want to solve problems in mechanics using this conservation of energy or potential energy. So first of all, we're going to have to identify the bodies that we want to study and identify all of the forces that are acting on the system of interest that we're trying to solve a problem with, right? The next thing we're going to do is determine that all of those forces are conservative. If they're conservative, then energy will be conserved, and then we can use energy conservation to solve the problem. For all of those conservative forces, we're going to have to choose a reference point, right? Because conservative energy is a relative quantity. Potential energy is a relative quantity. And we're going to have to determine a potential energy function. And then we can just apply the principle of energy conservation to that. So just to write that down again in the slides. So we start off with our conservation of energy, which essentially comes down to now the work done by non-conservative forces in going from A to B is the difference in the kinetic energy plus the potential energy in going from A to B, or often we'll write this as just E, the mechanical energy. So this is then the difference in the mechanical energy from A to B. And E is kinetic energy plus potential energy. That is the total mechanical energy. So if there's no conservative forces, this will be 0, and that will be delta E from A to B, or delta K plus U from A to B. So that's the change in kinetic energy. Well, let me not write this as individual terms, but that will mean that the kinetic energy at A plus the potential energy at A will be equal to the kinetic energy at B plus the potential energy at B. Or in other words, the sum of kinetic and potential energy at the starting point must be the sum of kinetic and potential energy at the ending point, or at the other points that you're interested in deriving a quantity for. So let's look at an example, which is the simple pendulum. Simple pendulum in contrast with what we're going to call the compound pendulum, maybe in this course, actually probably not in this course. But a simple pendulum is a pendulum where we have a mass hanging from a string from a fixed point. And the thing that makes it simple is that the mass is infinitely small. All of the mass is in that single point, and the string doesn't have a mass at all. So it's essentially just a single point with mass that is moving at a constant distance from the point where it's attached at the ceiling. So let's say we have a string that has a length L, the 1 meter here, and the mass is M, and we're letting this mass go from rest at an angle of 30 degrees. The question is now, what is the speed of this mass going to be as it crosses through 0 degrees? What's the speed at the lowest point? So if we go through our problem-solving strategy, so we've identified the body, and the body is to be studied. So in this case, the body that we want to study is just this particle. We're going to think about all of the potential energies and kinetic energies related to this particle. Because the string doesn't have a mass, we don't need to think about a kinetic or potential energy, because they're both going to be zero. We don't have to think about the ceiling. We don't have to think about anything else. So that's our system that we're interested in. Just that particle is the body that we're interested in. The forces that are working on this body are tension, and there's going to be potential energy. There's going to be gravity. And gravity is a conservative force. Tension is, in this case, going to be like a normal force, where the tension is always going to be perpendicular to the direction of motion. So tension is never going to do work in this case. That's not as universally true as it is for normal forces, but in this case, the tension will not do any work. Oops, wrong direction. So each force is conservative. In fact, for tension, it's a little bit of a trivial statement because there's no work being done at all. So it's not like it can conserve or not conserve energy. It doesn't affect the energy at all. And gravitational force is conservative. So all of our forces that are relevant are conservative. We can determine the potential energy for the conservative forces for gravitational force. And we already did. It's mg times h. And then we'll apply this principle of mechanical energy conservation. So if we go back here, we know that the potential energy is mg times the height. Let me write y. And we know that u initial plus k initial must be u final plus k final, where initial is at the starting point, where we know we're at rest. So this is going to be 0. And this is the lowest point. So at the lowest point, our kinetic energy won't be 0. But we can choose our reference point for the potential energy such that UF is equal to 0. If we pick that the final potential energy is 0, that means that the potential energy at the starting point will be mg times h, where h is the difference in height between the starting point and the lowest point. So we'll have that ui is equal to mgh. Ui is mg times h. So our expression becomes that mg times h, the kinetic energy is 0, is equal to, well, this potential energy we set 0, so that's 1/2 mv final squared. And now we can solve this for v final. First of all, what you'll see is that the masses drop out here. So v final will be 2g times the height times and everything under a square root sign. One thing you'll notice here is that there's no dependence on m. So if we look back at our pendulum, if we hang a mass of 1 kilogram here and let this swing, or we hang a mass of 100 kilogram or 15 kilogram, the speed with which the mass goes through the lowest point is going to be the same, regardless of the mass. That also means, of course, that this isn't just true for the lowest point. The speed will be the same all along. It will be the same regardless of mass, will be independent of mass all along the entire trajectory. So it's also going to take the same amount of time for a 1 kilogram mass to reach the other side as it does for a 15 kilogram mass. The time it takes to travel to the other side is going to be independent of mass as well, not just the speed at which it travels, because of course the same distances are at the same speed are traversed in the same times. The only thing we're still missing here is we still have this expressed in terms of h, in terms of the height, and of course we can relate the height to the initial angle and the length of the string. So the height will be the total length of the string, which is the distance to the lowest point here from the point where it's attached at the ceiling, minus the vertical component of the string when it's at 30 degrees. So minus the length times cosine 30 degrees. So what we're going to have ultimately is that the vertical, the speed is 2g times the length of the string, 1 minus cosine theta, because h is the total length minus the length times cosine theta, so L 1 minus cosine theta. Okay, so that's an example of using this problem solving strategy for conservation of energy problems. There's no non-conserving component to the work, so this non-conserving work is 0, and that's what allowed us to set the kinetic energy and the sum of kinetic and potential energy at the initial point and the final point equal to each other. So do we want U final always to be 0? No, I mean, in some cases it will make sense to set U final or to set U initial equal to 0. In some cases, maybe we don't want either of them to be 0. We didn't have to pick any of them 0 to begin with. We could have said, well, we could have set the potential energy at the top here equal to 0. So then the potential energy at the minimum, at the lowest point, would have been m times g times minus the length of the string. And then this here would have been at a potential energy m times g minus the length of the string times cosine theta. So we could have picked the reference point for the potential energy any way we would have liked. Now, if we had picked a different reference point, we would essentially have added a constant term to this potential energy, a constant term to this potential energy, and of course that wouldn't have made any difference in the mathematics of the problem. It would have just dropped out when we solved the equation. So we might as well do the easy thing and not even have that term show up there by picking or final potential energy or initial potential energy to be exactly equal to 0. So let's look at another problem, very similar. Well, actually, one of the things we can do before we move on to that. So this is A is the starting point. Essentially, all of our mechanical energy is in the form of potential energy. The kinetic energy is equal to 0. At the lowest point, we're in C here. So all of the equal amount of total energy is now in kinetic energy, and our potential energy is equal to 0. And of course, somewhere halfway, oops, the wrong one. Somewhere halfway, let's say at 15 degrees, or probably more likely 20 degrees or something higher, the kinetic energy and the potential energy are exactly the same, and they're each half of the total energy. And so we can tell that this is a problem where energy is conserved because this total energy bar is the same height everywhere. We can look at an example of a problem where there is energy non-conservation. That would be, for example, a helicopter that drops a package or a panel that falls from 1 kilometer height to the ground, and it has reached terminal velocity by the time it reaches the ground. So in this case, because there's terminal velocity, we know that drag is going to play an important role, right? Without drag, we cannot reach terminal velocity. Without drag, we would just continue accelerating. So the fact that we reach terminal velocity means that drag is playing a role. And so what we'll see is, in this case, the energy. So unfortunately, these bars are now, these charts or graphs are now shown one above each other instead of next to each other. But you can see that the total height of the E bar the total energy, the total mechanical energy is lower at this point than it is at this point. And the difference between the total mechanical energy is the amount of work that the non-conserving forces have done. So if we go back to this expression here, the difference in the mechanical energy, the total mechanical energy between A and B, is the work done by non-conserving forces to go from A to B. So of course it's more difficult to solve these kind of problems unless you know something about the work. You can't really solve these problems in the same way. So usually what we do here is we need more information to solve this. As you'll see in this problem, we know exactly what the initial potential energy is, the initial kinetic energy. So we know exactly what the initial energy is, the initial total energy. We know what the final total energy is because we can calculate the potential energy, we can calculate the kinetic energy because we're given the velocity. So we know the final total energy. So that allows us now to calculate the difference between the two, and that will be the work done by the drag force. That's the work due to the work done by non-conserving forces. So what you'll see in this problem, so this is free fall with drag in a sense. So we get that the work done by non-conserving forces from A to B is the difference in energy from A to B, and that will be the final kinetic, potential energy plus the final kinetic energy minus the initial potential energy plus the initial kinetic energy. And so the initial kinetic energy is equal to 0. We can set the final potential energy equal to 0. We'll have that this is 1/2 mass times the final velocity squared, and this will be mass times g times the height from which we drop the initial package. So that will be the change, and this will be the work done by non-conserving forces, or in other words, the work by drag as this object is falling. And so because we have h and the final velocity, we can calculate this. In the previous problem, we didn't have the final velocity, and we derived it from the fact that there was no work due to non-conserving forces. So that's where we're going to leave off today, and we're going to pick up again with probably exactly this problem on Friday. And I'm probably going to start with a problem that you may want to think about. Let's say you're standing here and you're throwing a ball right up in the air, and it's coming right back down. And if you cannot neglect air resistance, will the ball be, if you can neglect air resistance, you know the ball will have the same speed as it comes down as the speed with which you threw it up in the air. If you cannot neglect air resistance, will the speed be larger, smaller, or still be the same when the ball comes down as at the same height? So think about that by next lecture, by Friday, and we'll start off with that. Okay, that's it for today.